All right, everyone, lesson 4.3. Next lesson, we're going to be talking about graphs here. Not the type of graphs that you're used to seeing in math. We're going to be looking at different types of graphs, like in this example down here. This is a graph. I know it just looks like a bunch of lines and dots and letters. That is an actual graph in discrete math. So first off, the parts of the graphs are called the vertices and the edges. The vertices are the points. So A, B, C, D, and E would be your vertices. These are the points. Points on the graph. The edges you see are the lines. Okay, so here's an edge. From A to C, that's an edge. From C to D is an edge. From C to B is an edge. From C to E is an edge. From B to E is an edge. And from B to D is an edge. There's 6 edges in this one. I drew 6 lines there. Okay? And that's what this says here. The graph has 5 vertices and 6 edges, right? There's 5 points and 6 lines. So this graph represents, right here, 5 players on a high school basketball team, and the edges denote friendship. So who's friends with who? So which player has only one friend? So basically, if the points are connected, it means they're friends. So see A here? A's only friend is C. A is the person with one friend. How many friends does E have? E is connected to B, and E is connected to C. So E has 2 friends. B and C. Redraw the graph so that A has no friends. So what would you do to make A have no friends? You would just delete this line right here. If that line didn't exist, then A would have no friends. So like, if A was over here with no friends and no lines connected to it, okay, then A would have no friends. This graph is what's called a connected graph, because every point has at least one connection. Every point has a connection. And not only that, so like you could basically get everywhere you need to in this graph without ever picking up your pencil. So like if I needed to start drawing, right, I don't ever have to pick up my pencil to get to all the points in the graph. See that? So connected means that there's no points on an island. If the points were on an island, then I'd have to pick up my pencil to get to them, right? That's what connected means. So here's a connected graph. Every point could be traveled to. Here's a point that's not a graph that's not connected. A is on an island. Okay. Adjacent vertices are basically those that are connected with a line segment. So vertices that are directly connected. So remember that word adjacent from geometry? It means next to. So basically any points that are just directly next to each other, aka not just next to, but connected. So like in this graph down here, look, A is adjacent to B because they're connected, and also C, and also D, and also E. A is adjacent to everything. And if you look further, like B, so is B. B is connected to everything also. B is connected to A. See that line right there? We went over it twice. A is connected to B and B is connected to A. In this graph, all the points are adjacent. Because they're all connected directly to each other. You could do the same for C, D, and E also. But in this one, look, all the points are not adjacent. Like, oh, actually, they are too in this one. Yeah, they are. Look, I could get from A to C, A to E, A to D, and A to B, all directly. They're all adjacent. And the same thing goes for B, C, D, and E. They're all adjacent in both of those graphs. So that's what's called a complete graph. When every single point, all vertices or all points are connected to all other points, or all other vertices. The graph is complete. No matter which point you go from, you could get to every other point you need in the whole graph. Okay? And then finally, sometimes on this slide, sometimes you'll see a matrix representation. So basically this is binary, zeros and ones. Zeros mean they're not connected. Ones mean they are connected. So like we could draw this. So look, ready? So here's A. Let's look at this row. A has a 1 right here. So that means A and C are connected. Okay, see this row and column? They intersect there. So we could draw a graph that have A and C connected. Okay, then we got to go through the rest of the matrix. So now we look at B. B is connected to C and D. See this one right here? I'm drawing too many lines. That one and that one. Oh, and E. B is connected to C, D, and E. So if I draw B over here, it's connected to C. It's connected to D. And it's connected to E. Okay. Then we could do this row. C is connected to everything but itself. So we have to draw lines from C to every letter. So C goes to A, which we already have. Look, we already have C to A. We already have C to B, but we need to connect C to D and then also C to E. And then finally, well, our last two, D is connected to B and C, which we already have. We already have D connected to B and D connected to C. And then finally, we have E connected to B and C, which we already have both of those also. We have E connected to B and E connected to C, and that would be a picture of our graph. Your graph may look different. That's fine. It depends on where you put your letters. As long as you have all the connections in the right spots, that's all that matters. Like you could have rearranged these letters in different physical locations.